Hello, welcome back to our Chapter 3, Part 2. We're going to be picking up where we left off, and now we're going to be interpreting stem plot spread. So remember, this I believe is the third part of the three aspects when we're looking at visual representation or stem plots of data, right? The first part was our shape, then was location, and now we're on spread. So spread would include the range and interquartile, or IQR, which we're going to be covering in Chapter 4, and standard deviation and variance. All of these are definitely going to be covered in Chapter 4 and are a huge part. They need their own kind of chapter to go into, and they're covered very thoroughly in Chapter 4. And we're definitely going to want to focus on standard deviation and variance for sure, because that statistical measurement is used throughout the entire course. So if you want to make sure you're really honing in on something, 100% make sure you're honing in on standard deviation. But nonetheless, we can still talk about spread. When we're talking about spread, we're talking about the minimum to the maximum. So sometimes you're going to read online spread and range, and really they are different. Sometimes they're used interchangeably, and they shouldn't be. When we're talking about spread, we're talking about what is the minimum to the maximum value. We want to say what is the minimum, what is the maximum value. That is the spread. The way I like to think about it is if you have a peanut butter and jelly sandwich and you spread the peanut butter or jelly, whatever you're a fan favorite of. I'm a jelly person. I'd rather have more jelly than peanut butter. My wife, on the other hand, would definitely rather have more peanut butter, especially crunchy peanut butter. But that's a topic for another discussion. But when you're spreading peanut butter or jelly, regardless, you're going to want to spread the whole slice of bread. Right? You want it from top to bottom. You don't want it just in the middle or on the sides or anything. You want it spread from top to bottom. You want it from the minimum to the maximum. You want to spread the peanut butter or jelly throughout the whole slice. So for illustrative purposes, back to our example, we have a spread from 5 to 52. We would say the spread, if someone's asking what is the spread of this distribution, you go from the minimum value to the maximum value, so 5 to 52. So here's the second example of stem plot. So here we have data. Now as you can see, this data has decimals in it. And its decimals not going one decimal deep or to tens, it's going to the hundreds, right? So it's going to the hundredths value, and we want to create a stem plot for it. So the way we tackle this is we're going to tackle the stems as the ones place, right? Our significant, so we're going to tackle stems as the ones place, and then our leaves we're going to make them the tenths place. Now some of you might be asking, well, what about the other values there? Well, we're basically going to cut them off. We're going to cut off this extra digit. We're going to truncate it. Truncate is to shorten, cut off. So we're going to go from 1.47 to 1.4. No, we don't want to round in this situation, because if we round, then we're getting different values, and we're looking at data in a very precise way here. So we don't want to round it. That's why we just kind of cut it off. We're not going to use it at all. So here we have what the stem plot would look like, where we have our stems as the one place and our leaves as the tenths place here. And then when we want to describe this stem plot, we would say the center is between 3.4 and 3.7, which is underlined here. Don't get used to just saying the center, because we're going to want to report the median. We're going to want to report the median value. So the median value is going to be 3.4 plus 3.7 divided by 2, and that's going to give you your median value, which is going to be 3.55. The spread is going to be, once again, from the lowest to the largest value, so 1.4 to 4.4. And then the shape and mound, and as you can see, it's relatively symmetrical. With the data we have, maybe we have a slight negative skew here. It'd be kind of hard to tell because the sample size is so small to really judge. And then there's no potential outliers, but once again, outliers are going to be covered in Chapter 4. So here's a third illustrative example where we have 25 individuals. So here's our data for these 25 individuals, or maybe their ages. I don't remember exactly what this illustrated example was in, but nonetheless we have 25 data points to look at. When we put it on a regular stem plot, you kind of see it's really squished, right? So if we put our ones digit our tens digit, and then our ones, and then we do our stem plot. It's really squished. It's really kind of hard to tell the information that's going on here. So we're going to have to kind of what we call split it. We're going to have to split it up. We're going to have to divide this up a little bit so we can have a better shape. This is called a split stem. So on the first ones, we're going to have the stems hold leaves between 0 to 4, and on the second one stem, we're going to hold leaves 5 to 9, and so on. So that's going to, this is called a split stem plot, and this is what it looks like. So we have here where we have 2 1s as our stems, right, and then 2 2s, 2 3s, so on and so forth that you would need for the entire data point. And then on the very first part, we're only going to include values from 0 to 4, and then on the second line, only values from 5 to 9. And as you can see, this stays all the way through the rest of the stem plot. And as you can see now, the data is a little bit more spread out. And now you can kind of see a little bit more of a shape to it. And if you look at the shape, you can definitely see more of a negative skew. Remember your left foot, right? The big toe in comparison to the axis, right? It shifted, so we know it's our left foot, so it's a negative skew here. And you can see the negative skew is now a little bit more evident. The spread, once again, remember your spread is going to be your minimum value to your maximum value. We want to spread all the peanut butter or jelly all over a slice of bread, so it'd be 14 to 38, and we'd say the median is 29. So how many stem values do you need, right? So here we were talking about just using one stem value for some areas. Now we're doing split stems, so how many do you actually need? And truly the answer is it depends on the data you're given. But you're going to want to start somewhere between 4 and 12 stems. The less you have, the harder it is going to be to see any kind of shape with the data. The more you have, depending on the data set, you might be too spread out if you have too many. So you're going to have to find kind of a sweet spot in between. And sadly, the best way to do this is kind of trial and error. You might have to try different stem multipliers, try different splitting stems. You're going to want to look for the most informative type plot there is. Sometimes it'll be really simple to see how to set it up, and sometimes you might do a plot one way, and then you'll see, oh, I need to split it up because it's too congested, it's too crunched up, right? So here we have another example where we have the body weight in pounds of students in a class. So we have 53 students here, and this is their weight. So as you can see, you have all over the place from 110 to 260. Not sure if it's higher or lower than that, but there's a lot here. So when we're doing our stem and leaf plot for this, how are we going to set this up? So we got to think about this in a couple different ways. And so our data spreads from 100 to 260. So there must have been 100 in there I didn't see. And so if we did an axis multiplier of 100, we'd have 2 stem values, right? We'd have 100, so ones, and then 2s, and everything would be there. But that might not be enough, right? Because everything is between 100 and 260, so we don't have 2 stems and a lot of leaves. So we might not be able to tell a lot. So it might be too broad. If we had an axis multiplier with split stems, right? So 4 stems where we do 100 to 140, and then 150 to 190, right? We're splitting it up. There would be 4 there. That might do it. But once again, there's a lot of data points, and we might not see a true shape with that. But we can always go down to an axis multiplier of 10, which is what we do here in this next one. So here we have our example of those 53 individuals and their body weight, and we have an axis multiplier of 10 here at the bottom. And as you can see, it's a little bit spread out, but we have a better idea of the graph here. And if you kind of want to see, it would kind of look like that a little bit, right? It's not truly symmetrical. We got definitely some peaks right here, and we have a value way out here, right? So we're not sure if that's an outlier or not yet. Once again, that'll be covered in more chapter 4, but it is something to note, right? That this value does not really, it's really out here. Most of the values are over here, and this one's over here. So cause for concern, so it might be an outlier. But nonetheless, it looks better than if we just had 2 or 4 stems, because it's a little more spread out. So this one looks good. So we have a shape, we have now a positive skew, with a potential high outlier of 260, right? It looks like an outlier, but there's a specific way to find it, in which we have to find the interquartiles and interquartile ranges, and then find our fences, which goes over in Chapter 4. So for right now, we might say it's a potential outlier. If we actually do the math, though, I'll let you know it's not an outlier. It's close, but it's not. So, but for right now, it's a potential one. Here we have the location. The median is underlined, which if you want to see through my scribbles, is here. So about 165, which is where it'd be the median, is placed. The spread is 100 to 260 again. And that's how we describe our stem plot, based off shape, location, spread. So here we have how we can divide our stem values even more into quintuples. And here you have how we code for these stem values. So the star here is for leaves 0 and 1, T is for 2 and 3, F is for 4 and 5, S is for 6 and 7, and the dot is for 8 and 9. And this includes all the values. So you can see if you were to take the same values and you wanted to condense them even just a little bit more, there's definitely a way to do it as opposed to this way. So we can do a quintuple split stem values. If you use SPSS, which is a statistical analysis software, it can provide frequency counts with the stem plots as shown here. So here we have a mean age of 3 years, and you have this frequency as 2, so that means there's 2 of them at that level. It tells you the frequency with it. So we're going to go into frequency here a little bit, and the frequency is the count, or how many there are of that particular number or thing that you're measuring. And then you have what's called relative frequency, which equals to the proportion or percent of the total. And then you have cumulative frequency, which is the percent less than or equal to that level. So here we have our chart of which relative frequency we'll look at. So once again, we have ages here all the way down, and you'll have the relative frequency. So age 3, there's 2 people at age 3. So the relative frequency would be 2 over the total. So if you were to take 2 and divide it by 654, you'd get 0.3%. And then at the very beginning, the cumulative frequency, since this is the first one, is 0.3%. We're going to get cumulative frequency just a little bit more detail. If you look at relative frequency, if you move all the way down, it tells you how many people are age 5, how many people are age 8, 85, how many people are age 16, 13. And if you were to say, oh, there's 13 people at age 16, what is the relative frequency? What is that, what is the percent of that to the whole, right? Or the relative to the whole. So if you were to take 13 over the 654, you would get 2%. So this tells you this is 2% of the total. The relative frequency, when added up at the very end, will equal 100%. It should include everything. Cumulative frequency tells you in ascending order how the cumulative frequency at that specific point. So this one always keeps increasing in value. So if you wanted to know from age 11 down, what is the cumulative frequency? And from age 11 down, the cumulative frequency would be 73.4%. So 73.4% of the ages are 11 years old or less. And once again, as this increases, it will eventually add up to 100. If you want to think about relative frequency, cumulative frequency is the relative frequency at that point added together. So 0.3 plus 1.4 is 1.7. If you were to add up all of the first 4, so 0.3, 1.4, 4.3, and 5.7 would be 11.6. It's the cumulative frequency at that point. So now we have cumulative frequency tables with class intervals. When data is sparse, group data is into intervals. You can want to create 4 to 12 class intervals. Classes can be uniformed or non-uniformed, but you want to make sure that you have exact endpoints. So if you have class intervals from 0 to 10, it will include 0 but exclude 10, right? You don't want from 0 to 10 to be 1 and from 10 to 20 be another, because where does the value of 10 go on which part? You want to make sure you cut it off and make sure that each value is in a certain area. You're going to tally the frequency, calculate relative frequency, and calculate the cumulative frequency from there. All right, I have to stop the video here for a second. I'll pick it up in the next video. Will be relatively short. All right, have a good day.